Right now, above your head, there is a faint blur in the night sky that contains nearly 1 trillion stars and is moving toward us at approximately 250,000 miles per hour. That blur is the Andromeda Galaxy, stretching across roughly 220,000 light-years. It is larger than we once believed and vast enough to make our own Milky Way feel small. Tonight on Vellerin's Sleepy Space Mysteries, we slowly and gently unfold the true scale of Andromeda, not as a dramatic spectacle, but as a calm cosmic presence drifting through deep time. We will explore its distance of about 2.5 million light-years, its trillion stars, its massive dark matter halo extending far beyond visible light, and the quiet certainty that it is gradually approaching our galaxy. If journeys like this help you relax, please subscribe, like this video, turn on the notification bell, and consider joining our membership to support deeper explorations. Before we continue, tell us in the comments where you are listening from, so we can see how far this quiet signal reaches across Earth. When we say that the Andromeda Galaxy is about 2.5 million light-years away, the number can sound distant but abstract, like a statistic floating without weight. So let us slow down and gently unfold what that distance truly means. A light-year is not a measure of time. Even though it contains the word year, it is a measure of distance. It describes how far light travels in 1 year as it moves through the vacuum of space. Light travels at about 300,000 kilometers per second. That means in a single second, light can circle the Earth more than 7 times. In 1 minute, it travels about 18 million kilometers. In 1 hour, more than 1 billion kilometers. And in 1 year, that speed carries it roughly 9.46 trillion kilometers. Now pause for a moment and imagine multiplying that by 2.5 million. That is the gulf between us and Andromeda. The light entering your eyes tonight, if you are looking at that faint smudge in the constellation of Andromeda, began its journey 2.5 million years ago. When those photons left their stars, early human ancestors were just beginning to walk upright on the plains of Africa. There were no cities, no written language, no telescopes. Ice ages would come and go while that light was still traveling. Entire species would rise and vanish. And through all of it, those photons continued forward at 300,000 kilometers per second, never slowing, never stopping, until they finally reached Earth and quietly touched your eyes. To understand distance at this scale, it helps to step gradually outward. Light from the sun takes about 8 minutes to reach Earth. That distance, about 150 million kilometers, feels vast to us. It is 1 astronomical unit. Yet compared to 2.5 million light-years, it is almost nothing. If the distance from Earth to the Sun were shrunk to the width of a coin, the distance to Andromeda would stretch across continents. Our solar system, which feels immense in human terms, becomes a speck suspended in a much larger ocean. Andromeda is not only distant, it is also enormous. For many decades, astronomers believed its visible disk spanned roughly 100,000 light-years, similar in size to our own Milky Way. That estimate seemed reasonable. Through telescopes, the bright central bulge and sweeping spiral arms appeared contained within that scale. But as technology improved and surveys grew deeper, astronomers began to notice faint stars extending far beyond the previously measured boundary. The edges were not sharp. They faded gradually into the darkness. Modern observations reveal that Andromeda's visible stellar span approaches 220,000 light-years across. That is more than twice the width once assumed. It means that if you could travel at the speed of light, you would need 220,000 years to cross from one luminous edge of Andromeda to the other. Earlier estimates underestimated its true size because the outermost stars are faint and widely dispersed. They blend almost seamlessly into the background sky. Only with sensitive detectors and long exposures could astronomers trace these distant populations and redraw the galaxy's outline. When we compare this to the Milky Way's approximate diameter of 100,000 light-years, the difference becomes clear. Andromeda is not just slightly larger. The stellar disk extends roughly twice as far. That does not mean it contains exactly twice as many stars, but it does suggest a broader, more expansive structure. If both galaxies were placed side by side in darkness, Andromeda's luminous arms would stretch noticeably farther into space. And yet, even 220,000 light-years is only part of the story. A galaxy does not end where its brightest stars fade. Around Andromeda lies a vast halo of older stars and globular clusters extending even farther. Beyond that, an invisible halo of dark matter surrounds the entire system, reaching hundreds of thousands, even over 1 million light-years in influence. But tonight we stay with the visible span, the measurable disk that glows softly in photographs. 220,000 light-years, a structure so wide that light itself needs nearly 250,000 years to cross it. Imagine standing on a planet near Andromeda's outer edge and looking inward. The galaxy's central bulge would glow like a distant city of suns. Spiral arms would arc gently across your sky, woven with nebulae and clusters. The scale would feel overwhelming, yet from Earth, it compresses into a faint oval blur no wider than a fingertip held at arm's length. Distance shrinks giants. There is something calming in this realization. The universe operates on scales so large that even our largest numbers become stepping stones rather than endpoints. 2.5 million light-years, 220,000 light-years across. Light traveling at 300,000 kilometers per second for millions of years without interruption. These figures are not dramatic when spoken slowly. They are steady, measured, quietly immense. And when you look at Andromeda tonight, remember that you are not seeing it as it is now. You are seeing it as it was 2.5 million years ago. Its true present form remains unseen, still traveling toward us at roughly 250,000 miles per hour, closing the distance grain by grain across billions of years. The galaxy you observe is both real and ancient, present and past at once. So let the numbers settle gently in your thoughts. 2.5 million light-years away. Light racing at 300,000 kilometers per second. A visible span approaching 220,000 light-years, larger than our Milky Way's 100,000 light-year width. Vast yet drifting in silence. If you are still here, still traveling across these distances in your mind, type 1 in the comments so we know you are still listening. Now that we have gently unfolded the meaning of 2.5 million light-years, let us move even deeper into what it truly means to measure something so distant and so vast. When astronomers say that the Andromeda Galaxy lies about 2.5 million light-years away, they are not estimating casually. This number is the result of careful observation, patient calibration, and decades of refinement. The distance was first measured using a special type of star known as a Cepheid variable, stars that brighten and dim in a predictable rhythm. By comparing how bright they appear from Earth to how bright they truly are, astronomers can calculate how far away they must be. It is a quiet act of cosmic geometry. A pulse of starlight becomes a ruler stretched across intergalactic space. And through that method, the faint blur in the sky became not a nearby cloud, but a separate island universe floating millions of light-years beyond us. 2.5 million light-years is not just distance. It is delay. It means that every detail we see in Andromeda belongs to a time long before modern humans existed. If a star exploded there today, we would not witness it for another 2.5 million years. If a new star ignited in one of its spiral arms, that birth would remain hidden from us for epochs longer than our entire species has lived. Light carries information, but it also carries time. The universe we observe is always slightly older than the present moment. And in the case of Andromeda, the delay is so long that its light began traveling toward us before the first stone tools were shaped by human hands. To grasp the width of Andromeda, we must imagine not just a line drawn across space, but a slow crossing measured in light itself. 220,000 light-years from one luminous edge to the other. If you could ride a beam of light, moving at 300,000 kilometers per second without ever slowing, it would still take you 220,000 years to traverse the galaxy's visible span. Civilizations on Earth rise and fall in mere thousands of years. Entire languages disappear in centuries. Yet crossing Andromeda at light speed would require more than 200 millennia. That is the scale we are speaking of. Earlier generations of astronomers believed Andromeda was closer to 100,000 light-years across, similar in size to our own Milky Way. That estimate was based on the brightest regions visible through mid-20th century telescopes. The central bulge and main spiral arms glowed clearly, but the outer regions were faint and diffuse. As telescopes improved and digital imaging replaced photographic plates, deeper surveys began revealing stars extending far beyond the assumed boundary. Faint stellar streams arced around the galaxy, evidence of past mergers with smaller dwarf galaxies. The disk was not ending where we once thought it did. It was simply fading into darkness so gradually that our instruments had not yet traced its true extent. With better sensitivity came a revised measurement, stretching Andromeda's visible structure to nearly 220,000 light-years across. This expansion of measurement is not unusual in astronomy. Again and again, the universe has proven larger than our first estimates. We draw a boundary, then discover stars beyond it. We map a halo, then find it stretches farther still. In the case of Andromeda, the updated width changes how we compare it to the Milky Way. Our galaxy's stellar disk spans roughly 100,000 light-years. That makes Andromeda more than twice as wide in visible starlight. the spiral arms extend farther. The stellar populations reach deeper into space. Even from our distance of 2.5 million light-years, its true scale now appears more imposing. And yet, even this measurement has softness to it. A galaxy does not possess a hard edge like a planet. There is no sudden cliff where stars stop and emptiness begins. Instead, there is thinning. The density of stars decreases gradually. The brightness fades. Eventually, individual stars become so sparse that they blend into the background of intergalactic space. Measuring 220,000 light-years is therefore not the marking of a wall, but the tracing of a glow until it becomes too faint to distinguish. It is less like measuring the diameter of a coin and more like measuring the reach of a mist. If we compare Andromeda's diameter to the distance between our two galaxies, another perspective emerges. Its 220,000 light-year width is only a fraction of the 2.5 million light-years that separate us. Even a structure so vast still occupies only a small portion of the gulf between galaxies. The space between Andromeda and the Milky Way is not crowded. It is thin, filled with sparse hydrogen atoms and the invisible scaffolding of dark matter. Galaxies are large, but the emptiness between them is larger still. There is something soothing in these proportions. Our solar system orbits quietly within the Milky Way, itself 100,000 light-years wide. Beyond it drifts Andromeda, twice that size, separated by a distance more than 10 times its own diameter. Light moves steadily across that gulf at 300,000 kilometers per second, carrying images millions of years old. Nothing rushes. Nothing vibrates. Everything unfolds on scales so vast that urgency dissolves into calm inevitability. When you look toward Andromeda, you are measuring distance not with rulers, but with patience. You are seeing width not as a line, but as a glow stretched across 220,000 light-years. You are witnessing light that has traveled for 2.5 million years, arriving precisely now. And all of it moves according to quiet laws that require no drama to remain true. If you are still drifting through these numbers with me, still following the slow expansion of distance and scale, type 1 in the comments so we know you are still listening. Let us continue drifting gently through this immense scale, allowing the numbers to settle not as sharp figures, but as soft horizons. When we say that the Andromeda Galaxy is 2.5 million light-years away, we are really describing a separation so large that even light, the fastest thing in the universe, needs millions of years to bridge it. Light moves at about 300,000 kilometers per second. In a single second, it could circle Earth more than 7 times. In 1 year, it travels about 9.46 trillion kilometers. Multiply that by 2.5 million, and you approach the true scale of the gulf between our galaxy and Andromeda. It is not empty in the dramatic sense. It is simply quiet, a vast, thin expanse of space where atoms drift sparsely and gravity works patiently across unimaginable distances. Imagine freezing the universe in this moment. Somewhere in Andromeda, a star shines brightly. Its light radiates outward in every direction. Some of those photons will never encounter anything at all. They will travel forever into darkness. A tiny fraction, however, are aimed precisely toward us. They leave their star, pass between other stars in Andromeda, exit the galaxy's outer edge, and begin crossing the intergalactic void. For 2.5 million years, they continue forward at 300,000 kilometers per second, never slowing. When they finally arrive at Earth, they enter our atmosphere and strike a telescope mirror or perhaps your own eyes. That is the quiet miracle of distance. We are connected to something millions of years in the past by nothing more than a beam of light. Now consider Andromeda's true width again. Nearly 220,000 light-years across invisible starlight. Earlier astronomers thought it was about 100,000 light-years wide, roughly matching the diameter of the Milky Way. But deeper surveys revealed faint outer regions, delicate streams of stars stretching far beyond the bright central disk. These outer populations are dim and widely scattered, so early instruments simply could not detect them. As telescopes became more sensitive, Andromeda slowly grew larger on our maps. It did not physically expand. Our understanding expanded. The boundary we once imagined dissolved, and a broader, more graceful structure emerged. 220,000 light-years is difficult to visualize, so let us anchor it in time rather than distance. If a signal could move at light speed from one edge of Andromeda's disk to the other, it would take 220,000 years to complete that journey. Entire chapters of human evolution would unfold in that span. Ice ages would advance and retreat. Languages would appear and disappear. Yet within Andromeda, that crossing would still be incomplete. That is the pace of galaxies. Slow beyond comprehension, steady beyond urgency. And yet, in comparison to the 2.5 million light-years separating us from Andromeda, even 220,000 light-years feels modest. If you imagine the distance between our galaxies as a long stretch of open ocean, Andromeda's disk occupies only a portion of that expanse. The two galaxies are vast islands separated by a gulf more than 10 times the width of either one. The emptiness between them is so thin that if you were drifting through it, you might travel years without encountering even a single atom. Space is not crowded. It is spacious in the deepest sense of the word. There is also something humbling in how our perception of Andromeda changes with knowledge. To the naked eye, it appears as a faint oval smudge, barely noticeable unless the sky is dark and clear. Yet that small blur contains nearly 1 trillion stars and spans 220,000 light-years. Distance compresses enormity into something delicate. The farther away something is, the smaller it appears, no matter how vast it truly is. Andromeda's immensity hides behind its faintness. It does not demand attention. It simply glows softly in the darkness. If you were standing on a planet within Andromeda's outer arm, the galaxy would dominate your sky. The central bulge would shine like a luminous core. Spiral arms would arc overhead in rivers of starlight. From there, the Milky Way would appear as a distant blur, much like Andromeda does to us. Two great spiral systems observing one another across millions of light-years, each appearing small to the other, each vast in its own right. Andromeda's updated measurement of 220,000 light-years reminds us that the universe often exceeds our first assumptions. We draw lines around what we can see, and then improved instruments reveal faint structures beyond those lines. The cosmos does not shrink to fit our early maps. It grows as our vision deepens. Each refinement does not disturb the calm of space. It simply clarifies it. When you sit beneath the night sky and think of Andromeda's distance and width, you are contemplating scales so immense that ordinary concerns feel smaller by comparison. 2.5 million light-years of separation. 220,000 light-years across invisible starlight. Light racing at 300,000 kilometers per second, carrying ancient images through a silent void. These numbers do not rush. They do not flicker. They move with quiet inevitability. So let the scale remain gentle in your thoughts. A galaxy larger than ours, twice the width of the Milky Way's 100,000 light-year span. A separation so vast that its light began traveling before human civilization existed. And yet, here it is, arriving precisely now. If you are still here with me, still drifting through this immense and peaceful distance, type 1 in the comments so we know you are still listening. There is one more way to gently approach this scale, and that is to think not only about distance and width, but about proportion. The Andromeda Galaxy stretches close to 220,000 light-years across invisible starlight, while the Milky Way spans roughly 100,000 light-years in diameter. That means Andromeda's stellar disk extends more than twice as far from edge to edge. But diameter alone does not fully convey presence. When something doubles in diameter, its overall area increases by much more than double. A broader disk means more room for stars, more room for spiral arms, more room for ancient clusters orbiting quietly in its outskirts. Andromeda is not simply a larger circle drawn in space. It is a larger environment, a wider stage upon which nearly 1 trillion stars slowly move. Yet even with that immense width, Andromeda is still only a small fraction of the 2.5 million light-years that separate it from us. If you imagine the distance between our galaxies as a long, dark corridor, Andromeda's luminous disk would occupy only a short portion at one end. The remaining stretch is open, thin, and almost perfectly silent. In that silence, light travels at about 300,000 kilometers per second, carrying with it an image that is already 2.5 million years old by the time it reaches us. That means when you see Andromeda tonight, you are not seeing it as it is now. You are seeing it as it was long before recorded history, long before cities, long before even the earliest human civilizations. The idea that light itself is the measuring tool is one of the most beautiful aspects of astronomy. We do not stretch tape measures across space. We do not send physical probes to span millions of light-years. Instead, we observe brightness, rhythm, and motion. Certain stars within Andromeda pulse in predictable ways, allowing astronomers to determine how far their light must have traveled. Other methods compare the motion of stars and the redshift of light to refine that distance. Through patience and repetition, the figure of 2.5 million light-years emerges not as a guess, but as a carefully tested result. And yet, no matter how precise the measurement becomes, the feeling remains the same. The gulf is immense beyond everyday comprehension. Earlier generations underestimated Andromeda's true width because its outer stars are faint and dispersed. When telescopes were less sensitive, only the brightest central regions were clearly visible. The spiral arms glowed strongly, and beyond them the sky seemed empty. But with longer exposures and more advanced detectors, astronomers began to trace subtle stellar populations farther out. Streams of stars, remnants of smaller galaxies absorbed long ago, were found stretching across vast arcs. These discoveries gradually pushed the measured boundary outward, from about 100,000 light-years to nearly 220,000 light-years. And even that figure represents the visible disk, not the full gravitational influence of the galaxy. If you imagine traveling at the speed of light from one side of Andromeda's visible disk to the other, it would take 220,000 years. In that span of time, entire human civilizations could rise, flourish, and disappear. Languages would form and fade. Forests would grow and retreat. Yet within the galaxy, the crossing would still not be complete. That perspective slows everything down. It reminds us that galaxies operate on timescales so vast that urgency dissolves. There is no hurry in Andromeda's rotation. Its spiral arms turn slowly, completing a single rotation over hundreds of millions of years. Stars orbit the galactic center with calm inevitability, guided by gravity and inertia in a dance that has continued for billions of years. And still, across the 2.5 million light-year separation, Andromeda is moving toward us. At about 250,000 miles per hour, the two galaxies are gradually closing the gap. That speed sounds dramatic in human terms, but against millions of light-years, it is gentle. The approach will take billions of years. Long before the galaxies merge, Earth itself will have changed beyond recognition. The sun will age. Continents will shift. The merger will not be a sudden collision of stars crashing into one another. Instead, it will be a slow interweaving of gravitational fields, spiral arms stretching and blending over immense spans of time. Individual stars are separated by such enormous distances that direct collisions are unlikely. The event will be grand, but not violent in the way human imagination often pictures it. For now, the two galaxies remain distinct, separated by that quiet corridor of space. When you look at Andromeda as a faint oval blur in the sky, you are seeing something that spans 220,000 light-years across and lies 2.5 million light-years away. You are witnessing light that began its journey before humans had language. And yet it arrives exactly now, at this moment, as you sit in stillness beneath the turning Earth. There is comfort in that steadiness. Light travels at 300,000 kilometers per second whether we watch it or not. Galaxies rotate whether we measure them or not. Distances remain vast whether we comprehend them or not. The universe does not hurry, and it does not hesitate. It simply unfolds according to laws that remain consistent across millions of light-years. So let the numbers settle one more time in your mind. 2.5 million light-years away, nearly 220,000 light-years across. Larger than our Milky Way's 100,000 light-year span. Light racing steadily across the void for millions of years, and all of it visible tonight as a soft glow in the dark sky. If you are still here, still drifting gently through this immense scale, type 1 in the comments so we know you are still listening. Before we gently leave this part of our journey, let us gather everything we have measured and allow it to settle into one clear, quiet picture. The Andromeda Galaxy lies about 2.5 million light-years away. That distance alone stretches beyond intuitive thought. Light, traveling at about 300,000 kilometers per second, needs 2.5 million years to bridge the gap. Not minutes, not centuries, millions of years. When the light you see tonight began its journey, early human ancestors were still shaping simple tools from stone. Entire ice ages have passed while those photons crossed the void. What you observe is not Andromeda as it exists now, but as it was in a distant chapter of cosmic history. And yet distance is only half the story. Size is the other. Andromeda's visible stellar disk spans close to 220,000 light-years from edge to edge. Earlier astronomers believed it was nearer to 100,000 light-years across, roughly comparable to the diameter of our Milky Way. But deeper surveys revealed that faint stars continue far beyond the bright spiral arms. The galaxy does not stop abruptly, thins gradually. With improved instruments, astronomers traced these outer stars farther and farther outward, effectively doubling the previously assumed width. What once appeared contained turned out to be expansive. What once seemed similar in size to our galaxy proved significantly broader. If you imagine Andromeda and the Milky Way side by side, Andromeda's luminous arms would extend roughly twice as far. That difference may sound modest in words, but in cosmic terms it is enormous. Doubling the diameter means vastly more area, more stellar territory, more room for spiral structure. A galaxy 220,000 light-years across holds an environment of immense breadth. Light itself would require 220,000 years to cross that span from one visible edge to the other. In that time on Earth, entire civilizations would rise and vanish. Forests would grow and disappear. Mountains would erode slightly. Yet within Andromeda, that crossing would still be incomplete. Now consider proportion. The 220,000 light-year width of Andromeda is still only a fraction of the 2.5 million light-year separation between our galaxies. The gulf between them is more than 10 times the diameter of Andromeda itself. That means even something so vast occupies only a small portion of the intergalactic distance. The space between galaxies is not crowded. It is thin, sparse, and nearly empty. A few atoms per cubic meter drift through that region. Invisible dark matter weaves through it as well, shaping gravity on large scales. But compared to the density within galaxies, the void is profound. When you look at Andromeda with the naked eye, it appears as a faint oval smudge. That small blur hides nearly 1 trillion stars and spans 220,000 light-years. Distance compresses enormity into something delicate. If Andromeda were much closer, it would dominate our sky. Its spiral arms would arc overhead like luminous rivers. Instead, its immense size is softened by 2.5 million light-years of separation. What is gigantic appears gentle. There is also something humbling about how our understanding of its size evolved. The galaxy did not physically grow from 100,000 to 220,000 light-years. Our ability to see improved. As technology sharpened, faint outer structures became visible. Stellar streams, remnants of smaller galaxies consumed long ago, were discovered stretching far beyond the bright core. Each new observation nudged the boundary outward. The universe did not change. Our perception did. That pattern repeats throughout astronomy. We measure, we refine, we discover that reality extends farther than we first imagined. And still, across that immense gulf, Andromeda and the Milky Way are slowly approaching each other at about 250,000 miles per hour. That sounds fast, but across millions of light-years it is patient. The two galaxies will not meet for roughly 4 to 5 billion years. Long before that encounter, the Sun will evolve. Earth itself may no longer be habitable. The merger, when it comes, will be gradual. Stars are separated by such enormous distances that direct collisions are rare. Instead, gravity will reshape both galaxies over hundreds of millions of years, blending their structures into something new. For now, Andromeda remains distant, vast, and calm, 2.5 million light-years away, nearly 220,000 light-years across, larger than our Milky Way's approximate 100,000 light-year span. Light traveling at 300,000 kilometers per second, carrying ancient images through the darkness. The numbers do not rush. They rest quietly, like slow breaths across cosmic time. When you lift your eyes to the night sky and find that faint blur, remember what it truly represents. You are seeing a galaxy twice the width once imagined. You are seeing light that began its journey before recorded history. You are measuring distance not with rulers, but with the steady rhythm of physics itself. And everything about it unfolds slowly, without urgency, without noise. If you are still here with me, still drifting gently across these immense distances, type 1 in the comments so we know you are still listening. There is one final layer to measuring Andromeda that deepens the quiet meaning of these numbers. Distance and width are not just figures on a chart. They define perspective. When we say the Andromeda Galaxy is 2.5 million light-years away, we are also saying that everything we see there is ancient. The light reaching us left Andromeda long before modern humans existed. If a star near its core has already died in our present moment, we would not know for another 2.5 million years. In this way, astronomy is always an act of looking backward. The farther away something is, the deeper into the past we see. Andromeda is not simply distant in space. It is distant in time. Now return once more to the meaning of a light-year. Light travels at about 300,000 kilometers per second. In 1 second, it crosses 300,000 kilometers. In 1 minute, that becomes 18 million kilometers. In 1 hour, over 1 billion kilometers. In 1 year, nearly 9.46 trillion kilometers. Multiply that by 2.5 million, and you reach the true span between our galaxy and Andromeda. These numbers are almost too large to hold in the mind, so it helps to slow them down. Imagine counting 1 kilometer per second without stopping. It would take you more than 300,000 seconds just to match light's progress in a single second. Light speed is not dramatic. It is steady. It never tires. It simply continues. And that steady motion is what allows us to measure galaxies. Astronomers use the brightness of certain stars, the rotation of spiral arms, and the redshift of light to refine the distance to Andromeda. Over decades, those measurements have converged on the figure of roughly 2.5 million light-years. Not a guess, not a poetic exaggeration, a carefully tested value grounded in physics. Then there is the question of width. Nearly 220,000 light-years across invisible starlight. Earlier maps suggested about 100,000 light-years, similar to the Milky Way. But faint outer stars extended farther than expected. With better detectors, astronomers traced these dim populations outward, discovering that Andromeda's luminous disk is roughly twice as wide as once believed. That change in measurement did not mean Andromeda expanded. It meant our understanding sharpened. The galaxy had always been that large. We simply learned to see more of it. If you imagine Andromeda's 220,000 light-year diameter as a single glowing span, and then imagine the 2.5 million light-year gulf between our galaxies, you begin to sense proportion. The distance separating us is more than 10 times Andromeda's width. Even something so immense is dwarfed by the emptiness between galaxies. Space is mostly open, vast, silent, and gently curved by gravity. And yet, despite that enormous separation, Andromeda is moving toward us at roughly 250,000 miles per hour. That sounds dramatic, but across 2.5 million light-years, it is patient. The approach will take billions of years. When the two galaxies eventually merge, it will not be a sudden collision of stars crashing into one another. Stars are separated by such enormous distances that most will pass by without direct impact. Instead, gravity will slowly reshape both galaxies, stretching their spiral arms, blending their stars into a new, larger system. There is comfort in that pace. Nothing in the story happens quickly. Light travels steadily. Galaxies rotate slowly. Distances close gradually over billions of years. Even 220,000 light-years across is a measure of calm extension, not urgency. Andromeda's spiral arms turn over hundreds of millions of years. Individual stars orbit the galactic center with quiet consistency. The entire structure moves as one vast, balanced system. When you look at Andromeda tonight, you are holding all of that in a single glance. A galaxy twice the width once imagined. A disk stretching nearly 220,000 light-years. A separation of 2.5 million light-years bridged by light traveling at 300,000 kilometers per second. A glow that began its journey before human history. And perhaps the most remarkable part is how gentle it appears. From Earth, Andromeda is not overwhelming. It is subtle, a faint smudge in the dark sky. You must look carefully to see it. Its true size is hidden behind distance, its vastness softened by time. That is the paradox of the cosmos. The largest structures in the universe can appear quiet and delicate from far away. So let the numbers settle one final time. 2.5 million light-years away. nearly 220,000 light-years across, larger than our Milky Way's 100,000 light-year span. Light racing for millions of years to reach you, and all of it unfolding calmly, without hurry, without noise. If you are still here, still traveling gently through distance and time with me, type 1 in the comments so we know you are still listening. Inside Andromeda, the scale becomes more intimate, yet no less overwhelming. We often repeat the number calmly, 1 trillion stars, but it deserves to be felt rather than rushed past. A trillion is 1,000 billions. If you tried to count one star every second without stopping, without sleeping, without pausing for even a breath, it would take more than 30,000 years to finish. And that is only to name them, not to understand them, not to visit them, not to explore the worlds that may orbit them. Within this vast population, no two stars are truly identical. Some are faint red dwarfs, small and efficient, quietly burning hydrogen at a pace so slow they may shine for trillions of years. These stars form the quiet majority. They glow softly, often invisible to distant observers, yet they are steady and enduring. In Andromeda, billions upon billions of such stars create a background hum of starlight, a quiet foundation upon which brighter suns are scattered. Then there are stars like our own sun, stable, middle-aged, luminous enough to warm planets and shape atmospheres. If even a modest fraction of Andromeda's trillion stars host planetary systems, the number of worlds may itself reach into the trillions. Some would be frozen and silent, some scorched, some perhaps balanced delicately between heat and cold. The number is so large that probability alone begins to feel like inevitability. Andromeda also hosts massive blue stars, brilliant and short-lived. These giants burn through their fuel in only a few million years. Compared to the quiet lifespan of a red dwarf, that is the briefest flicker. Yet, in their short lives, they sculpt entire regions of space. Their radiation pushes against clouds of gas. Their eventual explosions scatter heavy elements outward, seeding future generations of stars with carbon, oxygen, iron, the very elements that build planets and life. So when we say 1 trillion stars, we are not describing a uniform field of light. We are describing a living structure, a layered population, ancient stars near the center, younger stars tracing spiral arms, dense clusters orbiting in spherical halos, quiet outskirts where stellar density thins into darkness. Astronomers often divide Andromeda's stars into populations. The older population 2 stars reside mostly in the halo and bulge. They are ancient, metal-poor, formed when the universe itself was young and heavy elements were rare. These stars have been shining for more than 10 billion years. They are time capsules preserving the early chemistry of the cosmos. Closer to the spiral arms, we find population 1 stars, younger and richer in heavier elements. These stars were born from gas already enriched by previous generations. Their composition hints at a galaxy that has recycled itself again and again, forming stars, losing stars, and forming them once more. The spiral arms of Andromeda are not solid structures. They are regions of higher density, like traffic waves moving through a crowded highway. Stars drift in and out of them over millions of years. Within these arms, star-forming regions glow in soft pink light where hydrogen gas collapses and ignites into new suns. Some of these stellar nurseries are so vast that they stretch across hundreds of light years. Entire clusters of stars are born together, siblings in light, sharing a common origin before gradually drifting apart. If we could move through Andromeda's disk slowly, gently, we would not see chaos. We would see order on enormous scales. Each star orbiting the galactic center, each cluster bound by gravity, each region participating in a quiet choreography that has been unfolding for billions of years. A trillion stars may sound violent in its magnitude, but in motion, it is surprisingly serene. The average distance between stars remains vast. Collisions are rare. Orbits are predictable. Gravity guides everything with patient inevitability. Inside this galaxy, scale does not shout. It hums. And as you imagine drifting through a trillion suns, still far from the bright central bulge and the massive black hole at its heart, notice how the enormity begins to feel less overwhelming and more rhythmic. A trillion is not chaos. It is structure repeated again and again across 220,000 light-years. In the next part, we will move outward into Andromeda's halo, where ancient globular clusters orbit like jeweled satellites, and where faint stellar streams reveal the memory of galaxies long ago consumed. If you are still traveling with us through this quiet sea of stars, gently type 2 in the comments. Beyond the luminous spiral arms, Andromeda's structure becomes older, quieter, and more revealing. Surrounding the main disk is a vast halo of stars, thinly scattered yet gravitationally bound, extending far beyond the bright lanes of visible light. Within this halo drift some of the most ancient objects in the galaxy, globular clusters. These are dense, spherical gatherings of stars, each containing hundreds of thousands, sometimes millions, of suns packed into a region only a few dozen light-years across. If the spiral arms feel like neighborhoods of ongoing activity, globular clusters feel like preserved relics, untouched archives of early cosmic history. Andromeda contains hundreds of known globular clusters, possibly more than the Milky Way. Each one is a tightly bound stellar sphere, ancient and metal poor, formed more than 10 billion years ago. These stars were born when the universe was young, when heavy elements were scarce and galaxies were still assembling themselves from smaller fragments. To observe a globular cluster is to look at a frozen memory of Andromeda's earliest chapters. Their stars move in complex orbits around the galactic center, tracing wide arcs through the halo, sometimes plunging closer to the core before drifting outward again. Inside these clusters, stars are far closer together than in the galactic disk. If you stood on a planet inside a globular cluster, the night sky would glow with thousands of nearby suns. Yet even here, despite the density, stellar collisions remain rare on human timescales. Gravity keeps them bound in a delicate equilibrium, a crowded but stable community that has endured for billions of years. These clusters are not temporary gatherings. They are survivors, But Andromeda's halo holds something even more subtle and haunting than globular clusters. It holds stellar streams. These are faint, elongated trails of stars stretching across tens or even hundreds of thousands of light years, barely visible against the darkness. They are the remnants of smaller dwarf galaxies that once orbited Andromeda and were gradually pulled apart by its immense gravity. Over millions of years, tidal forces stretched those galaxies into ribbons of stars, dissolving their cores and scattering their populations into long, ghostly arcs. Each stellar stream is a signature of absorption. Andromeda did not grow quietly or alone. It expanded by consuming smaller neighbors, integrating their stars into its own halo. This process is not violent in the cinematic sense. It is slow and inevitable. A dwarf galaxy drifts too close. Gravity stretches it. Its outer stars are stripped first. Then its inner regions unravel. Eventually, what remains is a faint stream marking where a once independent galaxy used to exist. Astronomers have mapped multiple such streams around Andromeda. Some wrap partially around the galaxy. Others arc outward like scattered threads. They reveal that Andromeda's trillion stars did not all form in one place. Many were inherited. Many were gathered over cosmic time through mergers that built the galaxy layer by layer. The smooth spiral we see today is the result of billions of years of accumulation, each absorbed system contributing its own stars, clusters, and chemical signatures. Even now, Andromeda continues this quiet process. Small satellite galaxies still orbit it, including companions that may one day become additional stellar streams. In this sense, the galaxy is not static. It is evolving. This halo is a dynamic environment, shaped by gravity's steady pull. Within the spiral arms themselves, star-forming regions glow softly in hydrogen light. Vast molecular clouds collapse under their own weight, forming clusters of new stars. Some regions stretch across hundreds of light years, producing massive associations of hot, blue stars whose ultraviolet radiation carves cavities in surrounding gas. These stellar nurseries ensure that Andromeda remains active, not merely a relic of ancient formation, but a continuing system of birth and renewal. So inside Andromeda, there are layers of time. Ancient globular clusters formed near the beginning. Stellar streams tracing mergers from billions of years ago. Spiral arms generating newborn stars even now. A trillion suns distributed across a structure that is both historic and ongoing. And through all of this, gravity governs quietly. It binds clusters. It stretches dwarf galaxies. It shapes spiral density waves. It guides every star in orbit around the center. There is no rush, no abrupt collapse, just gradual reshaping across immense spans of time. As we drift closer toward the heart of the galaxy, the density of stars increases. The spiral arms begin to curve inward toward a bright central bulge. There, at the core, lies something even more powerful. A supermassive black hole with a mass exceeding 100 million suns. It does not dominate the galaxy in visible light, but its presence shapes the innermost orbits of stars in profound ways. In the next part, we will move into that luminous central region and gently approach the quiet gravity of Andromeda's core. If you are still traveling with us through these ancient clusters and tidal streams, continue listening. The journey inward is about to begin. As we move inward from the halo and spiral arms, the light begins to thicken. The stars grow more numerous, more tightly arranged, and the structure of Andromeda becomes increasingly concentrated. The central bulge rises from the flat disk like a luminous swell, a dense sphere of ancient stars orbiting in complex, layered paths. Here, the population shifts again. Many of these stars are old, reddish, and stable, formed billions of years ago when the galaxy was still assembling itself from mergers and collapsing gas clouds. Their light blends together into a golden glow, soft yet intense, marking the gravitational heart of Andromeda. The density in the bulge is far greater than in the outer disk. Stars that might be separated by several light-years in the spiral arms are packed much closer here, though still not so close as to collide frequently. Gravity organizes their motion into elongated, tilted orbits, some tracing paths that resemble stretched ellipses around the center. The bulge is not perfectly spherical. Observations suggest it has a slightly elongated, almost bar-like structure embedded within it, guiding the inner spiral pattern and influencing how gas flows toward the core. And at the very center of this luminous concentration lies something invisible yet profoundly powerful. A supermassive black hole estimated to contain more than 100 million times the mass of our Sun. This object does not shine by itself. Black holes emit no light, but the region around it tells the story. Stars orbit at extraordinary speeds close to the center, their motion revealing the presence of an immense gravitational anchor. Only something incredibly compact and massive could hold them in such tight, rapid orbits. If we were to imagine approaching this black hole, we would not see a swirling vortex in the dramatic sense often portrayed. Instead, we would see stars moving calmly in predictable paths, though faster and more tightly curved than those farther out. The black hole's sphere of influence extends only a small fraction of the galaxy's total diameter, yet within that region it dominates completely. Its gravitational pull defines the innermost architecture of Andromeda's core. A black hole of this scale forms early in a galaxy's life, likely growing alongside the galaxy itself. As gas flows inward over billions of years, some of it feeds the black hole, increasing its mass. When large amounts of material fall inward rapidly, the region around the black hole can flare brightly as an active galactic nucleus, releasing intense radiation. Andromeda's central black hole, however, is relatively quiet today. It is not actively consuming large quantities of matter. It sits in a state of calm dormancy, exerting influence without spectacle. The presence of this black hole is not an anomaly. Nearly every large galaxy studied contains one at its center. There appears to be a relationship between the mass of the central black hole and the mass of the galactic bulge itself. In Andromeda, the ratio fits within this broader cosmic pattern. The galaxy and its black hole evolved together, shaping one another across deep time. Surrounding the core are dense star clusters and clouds of gas slowly orbiting inward. Some gas gradually spirals closer, potentially feeding the black hole in small amounts. Over vast spans of time, minor fluctuations in inflow can lead to brief periods of increased brightness. But compared to distant quasars or highly active galaxies, Andromeda's center remains subdued. Its power is steady, not explosive. What is remarkable is how stable the system remains despite its scale. 1 trillion stars, hundreds of globular clusters, tidal streams from absorbed galaxies, and a central black hole exceeding 100 million solar masses all coexist within a gravitational equilibrium. The motions are intricate but not chaotic. Each star follows its path determined by the combined mass of everything else. Each cluster remains bound. Each stellar stream slowly disperses but never disappears abruptly. Inside this galaxy, time stretches gently. The stars near the center may complete an orbit in tens of millions of years, while those farther out take hundreds of millions. Every orbit is part of a larger rotation, the entire galaxy turning as a unified system across billions of years. If we could step back far enough to see Andromeda as a whole, we would notice that nothing is hurried. The black hole does not devour recklessly. The bulge does not collapse inward. The spiral arms do not unravel. The tidal streams do not snap. Gravity holds everything in a patient balance. And so, at the heart of this trillion-star structure, there is not chaos, but inevitability. A massive anchor of curved spacetime, a luminous bulge of ancient suns, layers of motion nested within motion. In the final part of this journey inside Andromeda, we will gently weave together everything we have explored, the trillion stars, the absorbed galaxies, the ancient clusters, and the quiet central black hole, into a single perspective of scale and certainty. If you are still traveling with us through this vast interior, stay with the rhythm of the galaxy. If we now hold the entire interior of Andromeda in mind at once, the picture becomes less about individual features and more about continuity. 1 trillion stars are not scattered randomly. They are arranged by gravity into a layered system that has matured over billions of years. The spiral arms host ongoing creation. The halo preserves ancient memory. The stellar streams record past mergers, and the central bulge anchors everything around a black hole exceeding 100 million solar masses. It is not a chaotic assembly. It is an ecosystem of motion. Think again about the stellar streams, those faint rivers of light stretching far beyond the visible disk. Each one began as a smaller galaxy with its own stars, perhaps its own clusters, perhaps even its own planetary systems. Over time, Andromeda's gravity pulled them closer, stretching them into elongated arcs. Their cores dissolved. Their stars were redistributed. Nothing vanished. It was simply rearranged. This is how large galaxies grow. They accumulate, absorb, integrate. The trillion stars of Andromeda are not the product of a single event, but of countless encounters layered across cosmic time. Even the globular clusters, orbiting like ancient satellites, tell a story of survival. Some likely formed within Andromeda itself. Others may have been captured from smaller galaxies long ago. They continue circling in wide, slow orbits, maintaining their spherical shapes despite tidal forces tugging at their edges. Within them, ancient stars still burn steadily, unchanged for billions of years. Their light predates our solar system. Closer to the disk, star-forming regions continue their quiet work. Massive clouds of hydrogen gas collapse under gravity. As density increases, temperature rises, and nuclear fusion begins. New stars ignite. Around many of these newborn stars, disks of dust and gas may condense into planets. In this way, even as Andromeda carries the record of ancient mergers, it also carries the potential for new beginnings. A trillion stars does not mean the story is finished. It means the story continues. At the very center, the supermassive black hole remains a silent regulator. Though its sphere of influence is small compared to the full width of 220,000 light-years, its presence ensures stability in the innermost region. Stars near it orbit swiftly but predictably. Gas flows inward gradually. Occasionally, small amounts of matter spiral close enough to emit radiation before crossing the event horizon. But there is no catastrophic feeding frenzy. The black hole's mass, more than 100 million times that of our Sun, is immense, yet it does not dominate the entire galaxy. Instead, it coexists within a balanced structure shaped by distributed gravity across the trillion star system. What makes this interior remarkable is its patience. Stellar orbits unfold over tens or hundreds of millions of years. Globular clusters complete their circuits slowly. Stellar streams disperse gradually, never snapping but gently thinning. Even mergers occur over spans so long that no single star experiences abrupt disruption. The scale is immense, yet the tempo is slow. If we could stand somewhere in Andromeda's outer disk and look inward toward the central bulge, the view would be extraordinary. The core would appear as a bright concentration of golden light, dense and luminous. Spiral arms would arc outward like enormous rivers of stars, and beyond them, faint halos and stellar streams would trace subtle patterns in the darkness. Yet, despite the complexity, everything would be moving in harmony. Each star responding only to gravity. Each orbit shaped by the collective mass of all the others. This is what a trillion stars truly represents. Not just a number, but a gravitational network so vast that it sustains itself across billions of years. It represents energy continuously generated through nuclear fusion. It represents heavy elements forged in supernovae and recycled into new stars. It represents ancient remnants and newborn clusters existing side by side. Inside Andromeda, scale and inevitability blend together. The galaxy has grown through absorption and will continue evolving. This halo preserves history. Its spiral arms nurture youth. Its core anchors everything in quiet stability. And all of it drifts through space at immense speed, even now gradually approaching our own galaxy. There is something deeply calming in this realization. Nothing inside Andromeda is hurried. Nothing is random chaos. Gravity shapes everything with steady precision. Over billions of years, stars form, shine, and fade. Streams stretch and dissolve. Clusters orbit. The black hole remains. If you are still traveling with us through this vast interior of a trillion suns, gently type 2 in the comments, and let the rhythm of Andromeda continue carrying you forward. Now, as we let the full interior of Andromeda settle into a single, quiet image, the number 1 trillion begins to feel less abstract and more architectural. It is not simply a count of stars. It is a measure of structure. Each of those suns contributes to the gravitational fabric of the galaxy. Each adds its small pull to the collective balance. Together, they create a system large enough to stretch across roughly 220,000 light-years, yet stable enough to persist for billions of years without tearing itself apart. If we imagine drifting slowly outward from the central black hole, we would first pass through the dense bulge, where ancient stars glow in warm tones of orange and red. These are elders of the galaxy, some formed when the universe itself was still young. Their orbits overlap in layered patterns, tilted at various angles, yet all bound by the deep gravity at the core. The black hole, more than 100 million times the mass of our Sun, sits quietly at the center of this motion. It does not need to shine to assert its presence. The speed of nearby stars is enough to reveal it. Their rapid paths curve sharply, guided by an invisible anchor. Moving outward, the density gradually thins into the spiral disk. Here, the arms curve gently, not rigid structures but density waves passing through billions of stars. Gas clouds gather along these waves, compressed just enough for gravity to overcome pressure. In those regions, new stars ignite. Some are massive and short-lived, brilliant blue beacons that will end in supernova explosions. Others are small red dwarfs, destined to burn quietly for trillions of years. The disk is not static. It breathes slowly. Stars drift in and out of spiral arms over hundreds of millions of years, yet the overall pattern remains. Further outward still, the stellar halo becomes dominant. Globular clusters orbit like ancient lanterns, each a tight sphere of hundreds of thousands of stars formed in the earliest epochs of galactic history. They move on elongated paths that carry them far from the disk and back again, completing orbits that may take hundreds of millions of years. Around them, faint stellar streams trace the memory of absorbed dwarf galaxies. These streams are not bright or dramatic. They are delicate, almost transparent arcs of stars stretched thin by tidal forces. Yet they tell the story of how Andromeda grew, not through sudden creation, but through accumulation. The galaxy's trillion stars are therefore not uniform in origin. Some were born within Andromeda's own gas clouds. Others began their lives in smaller galaxies that no longer exist as independent systems. Over billions of years, gravity folded those histories together. The result is a layered structure. Ancient cores, younger disks, extended halos, and invisible scaffolding of dark matter binding it all. What makes this scale soothing rather than overwhelming is its predictability. A trillion stars move according to gravity's rules. No star decides its path. No cluster chooses its orbit. The entire system evolves through steady physical laws applied across unimaginable time. Even the supermassive black hole at the center is not a chaotic force tearing the galaxy apart. It is part of the equilibrium. Its mass influences only a small region compared to the full galactic span. Most stars, even those in the inner bulge, will never come close to it. Andromeda's internal motions are slow on human timescales. A star near the outer disk may take hundreds of millions of years to complete a single orbit around the center. Globular clusters move patiently along even longer arcs. Stellar streams stretch further and thinner with each revolution. All of it unfolds without urgency. If we consider the future, the interior of Andromeda will continue to change, but gradually. New stars will form in its spiral arms. Massive stars will explode, enriching surrounding gas with heavier elements. Some clusters may be disrupted by tidal forces. Additional dwarf galaxies may be absorbed. The central black hole may grow slightly if enough material drifts inward. Yet none of this happens suddenly. It happens over spans of time so vast that entire civilizations could rise and fall between one meaningful shift and the next. Inside this trillion-star system, inevitability replaces drama. Gravity binds everything into coherence. The halo remembers, the disk renews, the core anchors. And far beyond, unseen dark matter extends the galaxy's true reach even further than its visible stars suggest. So when we say that Andromeda contains 1 trillion stars, we are describing a self-sustaining structure of immense balance. It is vast, layered, ancient, and still evolving. It carries the memory of absorbed galaxies in faint streams of light. It holds globular clusters older than our Sun. It centers around a black hole more than 100 million times as massive as our star. And through it all, it moves calmly through space, slowly approaching our own galaxy across millions of years. If you are still traveling with us through this quiet architecture of 1 trillion suns, gently type 2 in the comments, and let the motion of Andromeda continue to carry you forward through the night. Far beyond the luminous spiral arms of Andromeda, beyond the bright clusters and glowing star-forming regions we can trace through telescopes, there exists something much larger and far more difficult to see. The visible galaxy, stretching roughly 220,000 light-years across, is only the lantern. Surrounding that lantern is a vast, invisible structure, a dark matter halo that may extend more than 1 million light-years from side to side. If the bright disk of Andromeda were the flame of a candle, the halo would be the silent darkness of the entire room holding it. We do not see this halo directly. It does not shine, reflect, or absorb light, but we know it is there because of the way gravity behaves. When astronomers measure how quickly stars orbit the outer regions of Andromeda, they find something unexpected. The stars at the edges move far too quickly to be held in place by the gravity of visible matter alone. If only the trillion luminous stars counted, the outermost ones would drift away into intergalactic space. Instead, they remain bound, circling steadily, guided by a hidden mass outweighing everything we can see. That hidden mass forms a spherical halo surrounding the galaxy, stretching outward into regions where the stars become sparse and faint. This halo is not a thin shell. It is a deep gravitational ocean, and the bright spiral arms are simply islands floating within it. In fact, Andromeda's dark halo is so large that it likely overlaps with the halo of our own Milky Way. Though the two bright disks remain separated by about 2.5 million light-years, their invisible outskirts may already be touching, interwoven through gravity long before the galaxies themselves visibly meet. This means the future collision between the Milky Way and Andromeda is not an event that will suddenly begin billions of years from now. It has, in a subtle sense, already begun. Gravity does not wait for light to announce it. It reaches quietly across distance, tugging persistently. Andromeda is moving toward us at about 250,000 miles per hour. That speed sounds dramatic when compared to earthly motion. A jet aircraft travels at a few hundred miles per hour. Even the fastest spacecraft humans have built move at tens of thousands of miles per hour. Yet 250,000 miles per hour is modest on cosmic scales. It is the natural consequence of two massive systems responding to each other's gravity over billions of years. Unlike most galaxies we observe, which appear to recede from us due to the expansion of the universe, Andromeda is close enough and massive enough that local gravity overcomes cosmic expansion. Instead of drifting away, it approaches. Slowly, inevitably, at 250,000 miles per hour, it will still take roughly 4 to 5 billion years for the two galaxies to fully merge. To put that into perspective, Earth itself is about 4.5 billion years old. By the time Andromeda fills our sky, our Sun will be nearing the later stages of its life. On human timescales, nothing about this is urgent. The continents will have reshaped themselves many times over. Species will rise and fall. Even mountains will erode and rebuild. The motion is steady, but it is patient beyond imagination. When the galaxies finally begin their visible encounter, it will not resemble a catastrophic explosion in the way movies sometimes portray. Galaxies are mostly empty space. Although Andromeda contains roughly 1 trillion stars and the Milky Way contains hundreds of billions, the typical distance between stars is measured in light-years. If our Sun were reduced to the size of a grain of sand, the nearest star would be another grain several kilometers away. That is how sparse galaxies truly are. As the two systems interpenetrate, the probability of direct star-to-star collisions remains extremely low. Individual stars are so widely separated that they will almost always pass by one another without contact. The real drama unfolds not in collisions between suns, but in gravitational rearrangement. Orbits will stretch and bend. Gas clouds will compress. New waves of star formation may ignite as interstellar material is stirred and shocked. Over hundreds of millions of years, the elegant spiral shapes of both galaxies will distort, unravel, and eventually settle into a new form, likely a large elliptical galaxy, sometimes nicknamed Milkomeda. But even that transformation will be gradual, unfolding over time spans so long that no single observer could witness it from beginning to end. In the next message, we will continue drifting through this future encounter, exploring what the night sky might look like during the merger and how our solar system may quietly ride along through the transformation. As Andromeda continues its slow approach, nothing in our daily lives changes. The stars above look steady, familiar, almost eternal. Yet across the deep silence between galaxies, gravity is steadily tightening its hold. 4 to 5 billion years from now, the first truly dramatic visual signs of this approach will begin to reshape the night sky. Andromeda, which today appears as a faint smudge barely visible to the naked eye in dark conditions, will gradually grow larger and brighter. Over millions of years, it will stretch from a misty patch into a luminous oval, then into a vast spiral filling more and more of the sky. Imagine stepping outside under a dark horizon and seeing not a small blur, but a second Milky Way arching across the heavens, its spiral arms clearly visible as broad rivers of light. The approach will not be a sudden rush. Even at 250,000 miles per hour, the scale of intergalactic distance makes the change slow beyond comprehension. Generations of stars will rise and fall in Earth's sky before Andromeda noticeably shifts position. But eventually, its gravitational pull will begin to distort both galaxies. Tidal forces, the same fundamental phenomenon that causes ocean tides on Earth due to the Moon, will stretch the outer regions of the Milky Way and Andromeda into long luminous arcs. Stars in the outskirts will be pulled into elongated streams, creating sweeping tidal tails that arc through space like cosmic brushstrokes. These tidal tails will not be made of chaos, but of motion carefully redirected by gravity's geometry. Individual stars will follow new paths, gently nudged into broader orbits around a shared center of mass. During the first close passage, the two galactic disks may swing through each other, their structures dramatically distorted. Gas clouds will collide far more often than stars, because gas is diffuse and fills more of the galactic volume. When massive molecular clouds intersect, they compress, and compression triggers star formation. Entire regions may ignite with new blue stars, hot and short-lived, blazing briefly in the darkness. Ironically, the collision of galaxies can create a renaissance of light. Where calm spiral arms once rotated in quiet balance, bursts of stellar birth may briefly illuminate the merging system. Yet even in this cosmic dance, the emptiness remains dominant. If you could somehow stand on a planet during the merger, you would not see stars smashing into one another like sparks. Instead, the sky would slowly rearrange itself over tens of millions of years. Familiar constellations would distort, dissolve, and reform. Bright star fields might appear in new directions as Andromeda's core passes nearby in cosmic terms. The supermassive black holes at the centers of both galaxies, one in the Milky Way and one in Andromeda, will eventually spiral toward each other as well. Andromeda's central black hole is far more massive than ours, containing over 100 million times the mass of the Sun. The Milky Way's central black hole is about 4 million solar masses. When galaxies merge, their central black holes do not collide instantly. Instead, they orbit one another at gradually decreasing distances, losing energy through interactions with surrounding stars and through the emission of gravitational waves. Over time, they will coalesce into a single, even more massive black hole at the heart of the newly formed galaxy. This merger will release enormous energy in the form of gravitational waves rippling through spacetime itself, though by then there may be no observers on Earth to measure them. And what of our solar system? The most likely outcome is surprisingly calm. The Sun, located about 27,000 light-years from the Milky Way's center, will continue orbiting through the evolving gravitational field. Simulations suggest that rather than being thrown violently outward, our solar system will probably migrate to a slightly different orbit within the merged galaxy. It could be flung farther from the center, placed in a more extended elliptical trajectory, or it might remain within a newly shaped stellar halo. The chance that another star will pass close enough to disrupt the planetary orbits is extremely small, though not zero. But even a close stellar pass, measured in thousands of astronomical units, would likely perturb distant icy bodies in the outer solar system more than the inner planets. Earth itself, if it still exists in recognizable form, would probably remain gravitationally bound to the Sun throughout the merger. By that time, however, the Sun will be approaching the end of its stable main sequence life. In roughly 5 billion years, it will begin to expand into a red giant, potentially engulfing the inner planets. So the galactic merger and the Sun's evolution unfold on similar timescales, two immense processes occurring independently yet overlapping in deep time. When we speak of collision, it is important to remember that it is not a crash, but a blending. Two spiral galaxies will lose their distinct forms and gradually settle into a single, larger elliptical system. The graceful spiral arms will fade, replaced by a smoother, more rounded distribution of stars orbiting in complex, layered patterns. The night sky, if any beings remain to see it, will be richer, denser, filled with unfamiliar constellations born from the intermingling of two ancient star families. In the next message, we will drift even deeper into the physics behind this merger, exploring why stars almost never collide, how gravity choreographs the encounter with mathematical precision, and why emptiness, not impact, defines the fate of galaxies. To understand why the future collision between the Milky Way and Andromeda will be more graceful than violent, we have to pause and truly absorb just how empty a galaxy is. When we say Andromeda contains nearly 1 trillion stars, the number sounds overwhelming. But those stars are separated by distances so vast that even light, moving at about 300,000 kilometers per second, takes years to travel from one to the next. If our sun were shrunk to the size of a marble placed in the center of a large city, the nearest marble representing another star would be several thousand kilometers away. That is the scale of separation we are dealing with. So when two galaxies merge, it is not like two dense clouds colliding head-on. It is more like two enormous swarms of fireflies passing through one another in a dark, open field, each light separated by immense space. Gravity, not impact, is the true sculptor of the encounter. Every star in Andromeda and every star in the Milky Way carries momentum, inherited from the original rotation of gas clouds billions of years ago. When vast clouds of hydrogen and helium collapsed under their own gravity in the early universe, even the slightest initial rotation became amplified as the material contracted. This is a simple consequence of conservation of angular momentum. When something spins and becomes smaller in radius, it spins faster. The same principle that causes a figure skater to spin faster when pulling in her arms also governs galaxies forming from collapsing clouds. That inherited rotation still defines the structure of spiral galaxies today. As Andromeda and the Milky Way draw closer, their enormous dark matter halos, each extending potentially over 1,000,000 light-years, interact first. These halos contain most of the mass of each galaxy, far outweighing the visible stars. Because dark matter interacts primarily through gravity and not through friction or collision, the halos will pass through one another smoothly, their particles barely noticing the encounter except through gravitational pull. This overlapping of halos gradually alters the trajectories of stars long before the bright disks make contact. The first close passage will distort the galaxy's shapes dramatically. Spiral arms will stretch outward into long tidal tails, some stars flung into extended arcs that may stretch hundreds of thousands of light-years into intergalactic space. Yet even these dramatic-looking features are simply stars following new gravitational pathways. No shock waves, no explosive detonations, just the steady mathematics of motion. Over hundreds of millions of years, these elongated structures may collapse back inward or disperse into a new stellar halo surrounding the merged system. Star collisions, while possible in principle, are extraordinarily rare because the stars themselves are tiny compared to the distances between them. Even in the denser central regions, where stars are closer together, direct impacts remain unlikely. What happens far more frequently are gravitational encounters at large distances. A star may pass another at a separation of several trillion kilometers, and even at that range, gravity slightly adjusts their paths. These cumulative interactions, multiplied across billions of stars, redistribute energy and angular momentum throughout the merging system. Over time, the elegant flat disks of the original spirals lose their organized rotation. Orbits become more randomized, and the final galaxy may resemble a vast elliptical cloud of stars moving in many directions rather than a neatly spinning disk. Meanwhile, the supermassive black holes at the centers of the Milky Way and Andromeda begin their own intricate dance. Each resides deep within a dense cluster of stars. As the galaxies merge, the black holes sink toward the new common center due to a process called dynamical friction. In simple terms, as a massive object moves through a sea of stars, its gravity slightly pulls those stars toward it, creating a wake of enhanced density behind it. That wake exerts a drag force, slowing the black hole and causing it to spiral inward. Over time, the two black holes will form a binary pair, orbiting one another at gradually shrinking distances. Eventually, after shedding orbital energy through interactions with surrounding stars and through gravitational radiation, they will merge into a single, larger black hole. This final merger will release a burst of gravitational waves powerful enough to ripple through spacetime across millions of light-years. Yet even that immense event would not tear apart the galaxy. Spacetime itself would tremble, but the stars would continue their journeys largely undisturbed. Throughout all of this, emptiness remains the defining characteristic. The merger is not destruction but transformation. The gravitational field reshapes itself into a new equilibrium. The luminous structure changes form, but the fundamental components persist. Stars continue burning hydrogen into helium. Planets continue orbiting their suns. The scale of time over which this unfolds is so vast that the word collision feels almost misleading. It is closer to a slow gravitational blending, two immense stellar populations gradually becoming one. And in this blending, there is continuity. The atoms in those stars were forged in even earlier generations of galaxies. The dark matter halos guiding their motion have existed since the universe was young. Motion never truly stops. It only changes pattern. In the next and final message, we will step back from the physics and rest in the deeper perspective of this event, reflecting on cosmic time, on motion that spans billions of years, and on what it means for us to exist within a universe where even galaxies drift together in quiet inevitability. If we step back from the mechanics and the numbers, from velocities and tidal forces and dark matter halos stretching over 1,000,000 light-years, what remains is something quieter and far more profound. Two galaxies, each containing hundreds of billions to a trillion stars, are slowly drifting toward one another across a gulf of 2.5 million light-years. They do not rush. They do not hesitate. They simply respond to gravity, the same gentle force that causes a dropped leaf to fall toward the ground. The difference is only scale. Andromeda moves toward us at about 250,000 miles per hour, yet even at that speed it will take roughly 4 to 5 billion years before the merger fully unfolds. That is almost the entire age of the Earth. When Andromeda's light first began its journey toward us 2.5 million years ago, early human ancestors were just beginning to shape stone tools. Entire civilizations have risen and fallen while that light traveled through intergalactic space. And still, the galaxies continue their approach without urgency. Cosmic time stretches far beyond the rhythms we know. A human life may last a century. Recorded history spans only a few thousand years. Even the lifespan of a species is often measured in a few million years. But galaxies evolve over billions of years. A single galactic orbit around the Milky Way center takes about 230 million years. Since dinosaurs walked the Earth, our solar system has completed just one trip around the galaxy. When the Milky Way and Andromeda finally merge, our sun will have completed perhaps 20 more galactic years at most. And by then, it will be entering the final stages of its life, expanding into a red giant. In that distant era, Earth may no longer be habitable. Oceans may have evaporated. The atmosphere may have transformed. Whether or not life persists, the galaxies will continue their motion regardless. There is something calming in that inevitability. The merger is not a catastrophe waiting in the wings. It is simply the continuation of motion that began billions of years ago when both galaxies first condensed from rotating clouds of gas within the young universe. The dark matter halos that now guide their paths have been shaping their evolution since near the beginning of cosmic history. Gravity has been quietly orchestrating this encounter from the start. When the two galaxies finally settle into one unified system, the result will likely be a large elliptical galaxy, smoother and rounder than either spiral that came before. The elegant spiral arms, those sweeping lanes of blue stars and pink nebulae, will gradually fade. In their place will be a vast, glowing sphere of stars orbiting in many directions. The night sky, if observed from within this merged galaxy, will be different. It may be denser with distant stars, more luminous in some directions. Familiar constellations will have long since dissolved. but the fundamental experience of looking upward into a sky filled with light will remain. And perhaps that is the deeper lesson. We often imagine the universe as violent or chaotic, but on the largest scales it behaves with extraordinary patience. Even collisions between galaxies unfold gently compared to the explosive events we see within them, like supernovae or gamma-ray bursts. The Milky Way and Andromeda are not racing toward annihilation. They are moving toward transformation. The individual stars, separated by immense distances, will mostly glide past one another untouched. Planetary systems will continue orbiting their suns. Dark matter, invisible and silent, will continue to shape the gravitational architecture of the merged galaxy. Nothing truly stops. Nothing truly freezes. Everything moves, but at speeds and over durations that dwarf human perception. And here, in the present, you are part of that motion. Right now, as you rest, the Milky Way is already drifting toward Andromeda. The solar system is orbiting the galactic center at about 220 kilometers per second. The Earth is circling the Sun at about 30 kilometers per second. The Earth itself is rotating at more than 1,600 kilometers per hour at the equator. Motion layers upon motion, all balanced, all steady. You feel still because everything around you shares the same movement. The same principle that makes us unaware of Earth's rotation makes us unaware of this galactic approach. Uniform motion feels like calm. When we imagine the future collision, it can sound dramatic, but in truth it is an extension of what is already happening. The dark matter halos are already overlapping. The gravitational pull is already at work. The story has already begun, and yet it unfolds so slowly that it poses no threat to our present moment. It simply reminds us that we live within a universe that evolves on scales of time and space far beyond daily concerns. In 4 to 5 billion years, the two galaxies will merge. In 10 billion years, the Sun will have exhausted its core hydrogen. In perhaps trillions of years, star formation across the universe will gradually cease as available gas is used up. Cosmic time stretches forward in quiet progression. But here and now, under tonight's sky, Andromeda still appears as a faint blur. Its trillion stars remain unresolved to the naked eye. Its massive dark matter halo remains invisible, and its approach remains imperceptible except through careful measurement. There is a certain peace in that. The universe is dynamic, but not frantic. It moves with immense scale and patience. And so, as this quiet cosmic journey comes to rest for tonight, consider the deep rhythm that carries galaxies across millions of light years and billions of years without haste. We are not separate from that rhythm. We are made of the same atoms forged in ancient stars, orbiting within one spiral galaxy that is gently drifting toward another. Motion is not something happening far away. It is the condition of existence itself. If you have reached the end of tonight's quiet journey through the invisible halo and the future collision, type 3 in the comments, and let's know you traveled all the way across deep time with us. Before we let this journey fully settle, there is one more layer to rest within, the scale of the invisible halo itself, and what it quietly tells us about where galaxies truly end. When we say Andromeda may have a dark matter halo extending over 1,000,000 light-years across, that number is not simply large. It is transformative. The bright disk we imagine, with its sweeping spiral arms stretching roughly 220,000 light-years, is only the luminous center of something far greater. Surrounding it is a gravitational sphere so vast that it dwarfs the visible galaxy several times over. Within this halo, the density of dark matter gradually decreases with distance, but it never forms a sharp edge. There is no clean boundary where Andromeda stops and empty space begins. Instead, its gravitational influence fades slowly into the cosmic background, overlapping with the halo of the Milky Way. In that overlapping region, gravity from both galaxies already intermingles, like two gentle tides crossing in a silent ocean. This realization changes how we picture the future merger. It is not two compact disks crashing together. It is two enormous gravitational ecosystems gradually blending. Long before the stars of the disks visibly distort, the dark matter halos have been interacting for hundreds of millions of years. Each halo contains far more mass than the visible stars combined. That hidden mass determines how quickly each galaxy rotates, how tightly its stars remain bound, and how strongly it pulls on its neighbor. Without dark matter, Andromeda's outer stars would not orbit at the speeds we measure. Without dark matter, the Milky Way itself would not hold its structure. The halos are not accessories. They are the true framework. When we look up at the faint blur of Andromeda, we are seeing only a small fraction of its total mass. The majority is invisible yet dominant. And this invisible majority is what ensures the merger will happen. Gravity at its core is simple. Two masses attract. The greater the mass, the stronger the pull. Across 2.5 million light-years, the combined mass of 2 trillion star systems, embedded within massive dark halos, exerts a steady acceleration toward one another. At 250,000 miles per hour, Andromeda approaches, but even that speed is modest compared to the immense distances involved. If you imagine shrinking the entire local group of galaxies down so that the Milky Way were the size of a coin, Andromeda would still be several coin widths away, drifting slowly closer. There is no urgency, only inevitability. Over billions of years, the approach will reshape both galaxies. Yet when we speak of billions of years, it is worth remembering how time stretches differently across cosmic scales. A billion seconds is about 31 years. A billion minutes is nearly 2,000 years. A billion hours is over 100,000 years. But a billion years is 1,000 million years. The merger will unfold over spans so vast that even entire species will come and go during its earliest phases. This perspective softens the word collision. The universe does not hurry. It evolves. In that evolution, stars will continue forming from compressed gas clouds stirred by tidal forces. New constellations will appear. Stellar populations from Andromeda and the Milky Way will mix until their origins are indistinguishable. If intelligent observers exist within the merged galaxy, they may look back and see faint stellar streams, remnants of the once separate spirals, and reconstruct the ancient encounter. They may study the motion of stars and detect subtle signatures of the two original systems. but to them it will be ancient history. Just as we study fossilized riverbeds on Mars or the faint afterglow of the early universe, they may study the fossil patterns of the Milky Way Andromeda merger. There is a quiet comfort in knowing that even events of galactic scale do not erase existence. They rearrange it. The atoms that form stars in Andromeda are the same kinds of atoms that form stars here. Hydrogen, helium, traces of heavier elements forged in earlier generations. When the galaxies merge, those atoms do not vanish. They continue cycling through stellar births and deaths, through supernovae, through planetary formation, perhaps even through life again. The universe is not fragile in the way we sometimes imagine. It is dynamic, but continuity runs deeper than disruption. And so, tonight, Andromeda remains a faint smudge in the constellation that bears its name. Its trillion stars glow softly, unresolved to the eye. Its dark matter halo stretches silently into space, unseen but powerful. Its motion toward us continues, steady and patient. And we, orbiting within the Milky Way, are already participants in this grand, slow choreography. Every second, the distance between the two galaxies shrinks slightly. Not enough to notice, not enough to matter to our daily concerns, but enough to remind us that stillness is an illusion shaped by scale. On human timescales, the sky appears fixed. On cosmic timescales, everything drifts. Galaxies move, stars orbit. Dark matter shapes the unseen architecture. Time flows not as a rush, but as a vast unfolding. As you rest now, the solar system continues its orbit around the Milky Way's center at roughly 220 kilometers per second. The Milky Way continues its gradual approach toward Andromeda. And far beyond, the universe continues expanding, carrying more distant galaxies away from us even as our nearest neighbor draws closer. Motion in every direction, balanced and continuous. This is the final layer of the invisible halo and the future collision. Not a story of destruction, but a reminder of belonging. We exist inside a galaxy that is part of a group, that is part of a web, that is part of a universe evolving across billions of years. The faint blur overhead is not separate from us. It is simply another expression of the same cosmic story. If you have followed this entire quiet journey through Andromeda's vast halo, its steady approach, and the distant merger awaiting billions of years ahead, type 3 in the comments and let us know you reached the end of tonight's calm voyage through deep time.